When dealing with simple harmonic motion, we're going to start to deal with specific terms that we utilize in actually measuring that motion. There's three main terms we're going to start to talk about, three main properties of simple harmonic motion, and they are the amplitude of that motion, the period of that motion, as well as the frequency of that motion. So we're going to talk about these in more detail moving forward. This will also be information we relate to waves, sound, and light as we, again, continue to move forward. So it's going to be really important to understand these concepts as best we can. When dealing with simple harmonic motion, we're going to really talk about two different examples. One is the mass spring system, which, as the name states, incorporates a mass suspended by a spring, and a pendulum, which is obviously some kind of mass suspended by a string or bar, anything that allows it to essentially rotate back and forth in this direction. And obviously the spring will travel up and down based on whether you pull it or push it up and then let it go. This will eventually oscillate, and this pendulum will oscillate much in this fashion. These are the two main examples we're going to deal with, so just get used to seeing them. There's some slight differences between them, but a lot of similarities. So moving forward with this chapter, we're going to be dealing with these two situations mainly. So that first term we were talking about was the amplitude. And it's important to realize that the amplitude is at the maximum displacement from the equilibrium point, the point where this mass or this object wants to be. That's that equilibrium point. So if we take a look here at this mass spring system, imagine these are the same exact spring, just three different points in time. So if we take a look at this middle one right here, we're going to go ahead and we're going to assume that that's our equilibrium point. So if we go ahead and assume our equilibrium point is right here, this is where it would like to be. Okay, it wants to be right there. Well, in this example, if I were to actually push that up to its maximum point of maximum displacement, it won't go up anymore. That's going to be my amplitude. And when I let go of it, it's going to begin to oscillate up and down, back and forth. And when it reaches the very bottom, it will reach a point down the bottom where it will go no further and it'll begin to travel back up. And in that case, that amplitude for the same mass spring system, these will be equal and opposite in direction. Okay, but that amplitude would be the same. If we take a look at the example of a pendulum, very similar. We have the equilibrium point right here. This is where this pendulum wants to be naturally. And if we were to pull it back and let go of it, it would, let's say if we pulled it back here, as soon as we let go, it would swing over here to this point, at which point it would return back and forth. And what we'd be talking about here in each of these cases, the amplitude would be that maximum displacement in either direction from that equilibrium point. And again, these would be equal and opposite generally. We'll talk about cases how this may increase or decrease, but overall these amplitudes will be the same. It should go in the same, it should go the same distance in this direction initially as it will in this direction. So it's measured in meters. It's a displacement, right? It's a distance. So we're talking about meters here. So it's important to realize that. The period and the frequency are slightly different in that they both involve time. Okay, both of them involve time in some way. Period, which is we use the variable t, capital T, to represent the period. That's the time taken to complete one cycle. So what that means is if I have, let's say I have an equilibrium point somewhere in the middle. Let's say that this spring naturally wants to be somewhere in between these two. So at some point I've pulled this up and I've allowed it to start oscillating back and forth. If that's where it would like to be, well, when I pull it up, it's going to have an amplitude in both directions. It's going to begin to oscillate back and forth. Okay, well, as it oscillates back and forth, the period is the time that it's going to take to go down and back up and return to its original position. So think of it as one cycle. It needs to start here. You're going to let go. It's going to go all the way up. It's going to come all the way back down. That's one period. Okay, so how much time it takes to complete one cycle to return to its original position. Because it's a unit of time, we're going to measure that in seconds. So if I take this spring and I pull it down and I let go and it takes 1 second to go all the way up and come all the way back down, my period is 1 second. Similarly, a pendulum is going to act in the same way. If I pull this pendulum back and I let go, it will swing this way, at which point it will turn around and come back. If that takes me 1 second, my period would be 1 second. It takes 1 second for one complete cycle to occur. Frequency, somewhat similar, but it's actually the number of complete cycles occurring in 1 second. So you're not looking at the number, you're not looking at how many cycles it completes. I apologize. You're looking at the number of cycles it completes in 1 second. You're not looking at the time it takes to complete one cycle. I apologize for that. So in a case here, if I were to pull this down and I were to let go, and it's going to complete number of cycles in 1 second, that's going to give me my frequency. Okay, so what I will do is instead of counting the time, instead of measuring 1 second, I'm going to count how many times, how many complete cycles occur within 1 second. So in the example of a mass spring system, my question in terms of frequency would be, in 1 second, in a given time of 1 second, how many complete up and down cycles would have occurred? Similarly with a pendulum, if I account for 1 second, if I have a stopwatch and I can measure 1 second of time, in that 1 second, how many times, how many complete cycles would the pendulum have completed? Okay, so it's measured in hertz, which is abbreviated capital H and lowercase z. And again, the hertz is just, the hertz, or a hertz, is just 1 hertz, apologize, is the number of cycles occurring in 1 second. So if you have 1 cycle in 1 second, well, your period, as we know from before, is 1 second, but your hertz is also 1 second because it takes 1 second to complete 1 cycle. Now, the period itself, we can go into a little bit more detail here. The period of a mass spring system, the way we calculate that is going to be slightly different than when we're dealing with a pendulum. The period of the mass spring system depends on 2 components. It's going to depend on the mass as well as the spring constant, okay, that K value of the spring. And it makes sense when you think about it, because if I have a very, very large mass attached to a spring and a very, very small mass, well, gravity is going to pull down on these differently, which means the spring is going to be acting against gravity differently. So it's fairly obvious that the mass is going to have some kind of effect. And the spring constant, if I have a much thicker spring, if I have a spring that's much harder to stretch out or much harder to compress, I should also get a different period as well. These are the 2 factors that affect this. And what we essentially have here is our calculation. If we want to know the period of a mass spring system, well, the period is going to equal 2 pi times the square root of the mass suspended by this spring divided by the K value of that spring. And as we said, it depends on mass and spring constant, and that's what this equation shows us, the mass and the spring constant. So, for example, just to show you a more realistic example, if we had some kind of spring here, and we had a mass suspended from it, and let's give these some values. Let's say we have a K value of 50 newtons per meter, and let's say we have a mass of 1 kilogram. Well, if I wanted to know the period of this, we know that the period is going to equal 2 pi times the square root of the mass over the spring constant. So 2 pi times the square root of the mass over the spring constant. And if we take our calculators and we plug this in, we will find that your period is going to equal 0.89 seconds. So that means it will take 0.89 seconds in order for this spring, once you pull it down, to make 1 complete cycle, to go all the way up and come all the way back down. Conversely, if I push it up instead and let go, it's going to take 0.89 seconds to travel down to its point of maximum displacement and then return to its original position. So that's how we calculate the period of a mass spring system. If we want to calculate the period of a pendulum, that's going to depend on slightly different factors. It's not the mass and the spring constant. We don't have a spring here. It's actually on the pendulum length and the acceleration due to gravity. So we'll look at the acceleration due to gravity first. If we have a pendulum here, we should realize that the reason it's going to move is because you have a certain force pulling down. And that force is going to be gravity, right? It's the force of the weight. It equals the object's mass times the acceleration due to gravity. That's what's going to pull this pendulum down. Well, if we look at Earth, we know that g, the acceleration due to gravity on Earth, is about 9.81 meters per second squared. Whereas if you're talking about the moon, we're talking about right around 1.6 meters per second squared. So our acceleration is different in these 2 locations. Therefore, our acceleration due to gravity and our weight calculation will be different. And overall, the force that's pulling this pendulum down will also be different. So the greater the gravity, the more force it pulls down, it's going to travel quicker. The less gravity you have, the less this weight pulls down, it's going to travel a little bit slower. It will accelerate more slowly as it begins to come down and return to its original location. And the length. Length is the other factor. I think you can imagine if you have a short amount of short spring, a short length, as this goes back and forth, you're generally going to have a different period than if you had a much, much, much longer length going back and forth. If it helps, think of maybe from TV shows or cartoons when that therapist is trying to hypnotize someone. Think about how fast that pendulum goes back and forth as they're trying to put you to sleep. And now think of like a wrecking ball when they're trying to knock down a building. If you've seen one in any kind of TV show, or if you've ever seen one in real life, you notice that it takes a very, very, very long time. Compared to maybe a hypnotist trying to hypnotize you, there's a big difference there. So if we look at the equation for this, it's very, very similar, but it's not based on the mass and the spring constant. It's not based on m and k. What it's actually based on, and for the case of a pendulum, is the length itself, as well as the acceleration due to gravity. Other than that, it's the same equation. So to show you an example, if instead of this mass spring system, we were to look at a pendulum that had, let's give it a length of 1 meter, and we typically measure this distance from the axis of rotation. This is the point that this pendulum will oscillate around, to what's known as the center of mass. We've discussed that when we talked about forces. The center of mass. So you don't really measure from the top of the string to the bottom. You typically measure from that pivot point to the actual center of mass. So it's not a huge difference, but you should be aware of that when you make your calculations. And let's assume that this is on Earth. So if it's on Earth, we know that the acceleration is 9.81 meters per second squared. So if we take a look at our equation right here, we know that the period for this pendulum on Earth is going to be 2 pi, and we're going to multiply that by the square root of our length, which is 1 meter, and we're going to divide that by our acceleration due to gravity, which is 9.81 meters per second. If you take your calculators and you plug that into it, you're going to find that this period is essentially 2 seconds. Probably a little bit higher if you calculated correctly, but we can round and say it's about 2 seconds. So on Earth, if you have a pendulum that has 1 meter, it's going to take 2 seconds to make one complete cycle. So its period will be 2 seconds. Now it's important to realize, in the case of a pendulum, none of the factors affecting it, as you can see by this equation, are mass. So I could take a large, massive wrecking ball with 1 meter of distance between its pivot point and its center of mass, and it will take 2 seconds in order for that to complete one cycle. Or I could take something very light, like a small marshmallow, and assuming we're neglecting air resistance and things like that, as we typically do, if I put a small marshmallow on the end of a 1 meter string, that will also take 2 seconds. Mass does not account for any differences in the period of a pendulum. We only care about the length of that pendulum and the acceleration of gravity based on where you're actually analyzing.